try to implement an algorithm to compute this gradient of z, the nabla z. So this is the definition of the one component of this vector. This is a vector, this is a vector. So one component of the vector, the component j, is equal to this. So first, what I need to do in order to evaluate gi, the derivative of gi, is to compute the sum here to obtain the value of my y. If I don't have the value of my y, I cannot compute this function. So I will do a forward pass. I will go from these nodes here, and I will compute the values on the y here. So this is what this term is about. Okay, I have my values assigned to my variable y here, and I can store this intermediate result in the node. And then I can continue. I can also compute z, but for computing the quantity that I'm looking for, this gradient, I don't need z here in this formula. So now, what can I do? I will start from at the end of the computational graph, and I will go backward. So now I can evaluate the derivative of my function gi at yi. This is the term of yi. It has been computed before during the forward pass. And I can start the intermediate result. This part, I will start it on the edge. And then I continue. I can compute this quantity here, which will be associated to one edge. So it's the derivative of the function f from node g to I, evaluated at its g. And I can start it here. And what we can see is that this expression is the product of this term that has been computed and stuck on this edge, and this term that has been computed and stuck on this edge. So I'm doing the product of the value of this edge with this edge. And so to compute this component of the gradient, I can convert the problem of computing this linear approximation, of computing the gradient, as a graph traversal algorithm. I will start from the end, and I will compute these expressions edge by edge, and then I must multiply these expressions together and sum them. So this expression is the product of the value associated to this edge with this edge, plus the value of this edge with this edge, plus the value of this edge with this edge. And is there a way to do it more efficiently? So let's see. I will not use the equation here. I will just add one layer to this graph. And so to compute the gradient of the output with respect to one input, it's a graph traversal problem. I must go over all the path from this node to this node. And so I can compute the intermediate result on this edge, and then I do the product of these three values. And if we look carefully, after computing the gradient with respect to this node, then I will compute the gradient with this node. But the value associated with these two nodes have already been computed before. And instead of just computing one time and then erasing the information, I should reuse this information in a given way. And backpropagation is a very effective algorithm to do it. So instead of doing all the path from this node to this node without looking at the other nodes, I will do it in a systematic way based on dynamic programming. And so from this node, I will compute the values of the derivative of the function evaluated at the values of these variables. And I will do it for each edge coming from this node. Then I go to the next layer. I can compute all the information here, and I can already do my product so that this edge with this edge, I can compute the product here too. So at this point, I have all the information. I don't have to look back at the previous step to implement this idea of dynamic programming. And now I have the last layer that I can do. And so I'm reusing all the information. I'm not erasing or recomputing any information. It's done in an effective way. And backpropagation was proposed by Sepa Linema in 1970. And it was proposed in the automatic differentiation community. So instead, physicists were tired of computing their derivative by hand. They wanted the programs to do it for them. So there was a lot of work on automated differentiation. And this master student found this algorithm to do it efficiently based on dynamic programming. And the first time it was applied to training neural network, it was by Homenhart and Hinton in 1986. And so there was a lot of time between the two to really understand that a neural network, like we just saw in the first lecture, can be interpreted as a computational graph, and so backpropagation would be useful to compute the gradient. It was 16 years between the two publications. And now what we are saying is that we are doing differential programming. When we are creating this graph that are all differentiable, that we can compute the impact of any parameters on the loss function at the output by using this technique and by using derivative. Now, every time we are programming, we have this notion of differentiable underlying the architecture. And we can have very complex model like the ResNet here, which is end-to-end differentiable.